Consider the list of 6 substances with their formula and boiling points. Okay, so we've got water, ethanol, bromine, iodine, and then ammonia and phosphine. Okay, and we've got their formulas and then their boiling points. The first question says, define the term boiling point. Now, boiling point is when you go from a liquid. You can think of if you're boiling water on a pot, you'd go from liquid to gas. But you can't say that that's what boiling point is. I wish we could. You can't just say it's when a liquid turns into a gas. What you rather have to do is the following. Is we need to go into the deeper meaning of what happens when water boils or when any substance boils. So let me explain. So here we've got a pot of water one day. We're busy boiling some water. So in here we've got water molecules. Okay, now we start increasing the heat, and so what happens is that even before we get to 100 degrees, some of the water is already going to start turning into gas. That can happen. Think about a swimming pool that evaporates. You don't only get the water moving into the gas phase when it boils. There's also things like evaporation and things like that. So as soon as you start increasing the temperature, even before it gets to 100, some of these molecules are going to start turning into the gas phase. And that's why before the water boils, you'll see steam being produced when you're boiling water on a stove. So some of the water molecules are going to be converted into the gas phase. Okay? And so over time, you're going to start seeing water developing over here. Now, this is a gas now, whereas this is still the liquid phase. Okay? But in the early stages, you're still going to have there's going to be loads of water in the liquid phase, and there's not going to be so much gas over here. But as time goes on and the temperature starts increasing, these molecules they gain a lot of energy, and so they can start escaping from the liquid, and they can start escaping into the gas phase. Now, this gas phase is starting to fill up. Can you see there's more gas molecules that are starting to fill up? Those gases are going to start creating a pressure. That pressure is called vapor pressure. Vapor pressure. Gases create vapor pressure. Now, what we need to understand is that in the world we live in, there is gas. So there's gas over here already. You know, the air that we have around us. Now, that gas is also exerting a pressure. You know, we've got the atmosphere. Now, there's this amazing thing that happens when the pressure due to this gas or this vapor pressure becomes the exact same as the vapor pressure. Becomes the exact same as the atmospheric pressure. So this isn't the definition, I'm just writing some notes for you. When the vapor pressure of the gas becomes the same as the atmospheric pressure, we get boiling. Okay? So that is what happens. So what is the real definition? Sorry, I meant to move these onto these slides over here. So you can see the marker location. So boiling point is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Okay, so that is what boiling actually is. Now, the next one, and remember these questions do carry on, okay? We've got that slide over there and that one over there. So it says, explain why the boiling point of iodine, now remember iodine is diatomic, they have showed us that, is much higher than that of bromine, okay? By referring to the intermolecular forces. Ooh, this is a good one. I'm very happy that they're asking this question. So what we're going to find is that, and I'm going to go through this in detail with you, but these are both going to be these are both going to be non-polar molecules. And maybe you've come across questions like this before where both of them are going to be non-polar, so it's only going to be London forces, but then there's still going to be a massive difference in their boiling point, and that has got to do with the molecular mass. So this question is all about, and maybe you've been wanting to go over this, or maybe you've come across this before and you haven't understood it, but it's the effect. This is what this question is going to be about. The effect of molecular mass on London forces. Okay, it's really interesting. So let's get into it. So our first step will just be, I want you to just be convinced that bromine and iodine are both non-polar molecules. So let's go draw their Lewis diagram. So for bromine, we know that bromine is in group 7. So this is a pretty easy Lewis diagram, so I'm not going to waste too much time here. But if you had to go draw its Lewis diagram, you would eventually end up with that. Now, because these are the same atom, they're going to have the same electronegativity. So these electrons here are not going to be more to the left or more to the right-hand side. And so this molecule is not, let's just write here, it will not have a dipole moment. So no net dipole moment. Okay, so that means it's non-polar. It's non-polar. Let's just say here, therefore, non-polar. So if you had to put another bromine molecule next to that, because remember, whenever we look at intermolecular forces, it's always about the forces between molecules. So here's the first molecule. Let's just do that a little bit better. And then here's the second molecule. And so if you have two non-polar molecules next to each other, then the intermolecular forces are London forces. London forces. Okay, I'll leave this as an exercise for yourself, but if you had to go do the same thing for iodine, well, I'll just quickly draw it out for us. So iodine would look exactly the same. Also got the same amount of, everything's going to be the same. Okay, so once again, no net dipole moment, so this is a non-polar molecule. Let's just draw this part a little bit better. So this is a non-polar molecule, and this is also a non-polar molecule. So let's just say this is our first one, here's our second one, and so in between here, we are once again going to have London forces. So both molecules, iodine as well as bromine, are going to have London forces between their molecules. So why then would the difference in boiling point be so significant? Why is iodine so much more difficult to boil? Look how large the boiling point is compared to bromine. So why is it that these forces are so much more difficult to overcome compared with these London forces over here? Why are these easier to overcome and these ones are difficult to overcome? Well, what is going on there? Well, that is where we need to look at this part of intermolecular forces, which deals with how do London forces change with molecular mass. Well, I think what would be nice to do now is just to remind ourselves, how do London forces work in the first place? So let me go draw a made up molecule, which is called A, or A squared, or A2, whatever. So there's a molecule, and here's another one. We always draw two because we want to look at the forces between the molecules. Okay, now at the moment, these two atoms are exactly the same. So this is a non-polar molecule, and this is a non-polar molecule. So we definitely have London forces between the molecules. But how do London forces, what are they actually? Well, I'm not sure if you know this, but electrons are continuously moving. Electrons are never standing still, they are always moving. So in this molecule over here, you've got these electrons, okay? Now, at any given moment, the electrons could be in a slightly different position. So maybe for a few split seconds in this molecule over here, the electrons there seem to be more electrons on the left-hand side compared to on the right-hand side. So maybe these electrons are even moved a little bit that way, and the electrons are just more towards the left-hand side of the molecule. So what that does is it creates a little bit of a negative on this side because electrons are negative, and that leaves this side to be a little bit more positive. And at the same time, that same process is happening over here. Maybe all of the more electrons are tilted towards the right-hand side. Let's just put these a little bit closer. So maybe you've got more electrons towards the right-hand side of the molecule, and so this part becomes slightly negative, this part becomes slightly positive. Now, that causes an attraction force over here because you've got a negative and a positive. And then over here again, you've got a positive and a negative. So that creates some type of attraction. So these electrons are continuously moving at any single moment. And what it's doing is it's just creating these positives and negatives the whole time. We call these temporary. They are not permanent. So maybe in the next split second, the electrons would move somewhere else. And so you're continuously developing these positives and negatives. So we call it like a temporary dipole. So it's creating a temporary dipole, okay? That is what London forces are. It's just due to the random movement of electrons within the molecule. The electrons are not staying still. So how does molecular mass come into everything? Well, now scientists have observed that heavier molecules have stronger London forces. Now, let me quickly explain why that is. So if we look at, and then I just want to add something else here, this is due to a higher chance of asymmetrical, I will explain this now, asymmetrical charge distribution. Okay, so let me explain what I mean. So if you have a molecule like this, A and A, or it's got two atoms A, and let's say the electrons are perfectly in the middle, okay? And it just looks absolutely perfect. Now, if those electrons are perfectly in the middle like that, we will call this a symmetrical. That is symmetrical. You know symmetry? That's what they mean, symmetrical, okay? And if you have symmetrical molecules like this, like let's say you have another symmetrical molecule, then there will actually be no London forces, because if these electrons are perfectly in the middle, then you cannot create a negative and a positive side, so there would be no London forces. But when the electrons start moving a little bit more to one side, for example, so you get a situation like this, then that is called, and let's do this one like this, that is called asymmetrical, which means it's not symmetrical. So now you'd be creating a more negative when you've got more electrons on the side, and then this would become a positive, and then here you'd create a negative, and here you'd create a positive, and so then you would get some type of attraction force over here, and that's your London force. Okay, so London forces can only happen when you've got asymmetrical charge distribution. Now, what scientists have discovered is that when you have heavier molecules, by the way, have more electrons. I'm not saying that they're heavier because of the electrons, but if you just look on your periodic table, for example, bromine has a mass of 80, and it has 35 protons and 35 electrons, whereas iodine has a mass of 127, and that means it has 53 electrons and 53 protons. So the general, what we can see is that heavier molecules have more electrons, okay? So heavier molecules have more electrons, and scientists have discovered that they have stronger London forces, and this is due to a higher chance of this happening over here. So you can summarize this for yourself is that heavier molecules have more electrons, okay? And once again, I'm not saying that they are heavier because of more electrons. We know that electrons don't have any mass, but if you just look on the periodic table, you'll see what I'm talking about. Heavier molecules have more electrons. Having more electrons increases the strength of London forces due to higher chances of asymmetrical charge distribution, okay? And it's when you create those asymmetries, that's when you start getting London forces. And when you've got heavy molecules with lots of electrons, it's very easy for them to create these asymmetries. So the strength of the London forces actually becomes stronger. So that's the background. Now I'm going to just show you how to actually answer the question. So it says that explain why the boiling point of iodine is so much higher by referring to the intermolecular forces. So for both of them, it's London forces. So let's start by saying that both bromine and iodine only contain London forces. They don't have other things like hydrogen bonding or anything like that, okay? You're then going to say that iodine is a much heavier molecule, is a heavier / you could also say larger molecule than bromine. You can then say that London forces are stronger in heavier molecules, okay? And then you can say therefore, more energy is needed to overcome the forces of attraction in iodine molecules compared to bromine molecules. Compare ammonia and phosphine, okay? So here we've got ammonia and phosphine, and explain the difference in their boiling points. Step 1 with any of these questions would be to draw the Lewis diagrams, because from that you can determine is it polar, non-polar, and from non-polar and polar, you can determine are there London forces or is it dipole-dipole forces, Is it maybe hydrogen bonding? And so the Lewis diagram is a good starting point. So I'll start with NH3. So we know that N is in group 5, so that's 5 valence electrons. I'm just going to say 5 electrons. And then there are 3 hydrogens, and each of those is going to have 1 valence electron. Okay, so there's a total of 8 valence electrons. So you've probably done NH3 before, but you're going to put H's like that, for example. And then you're just going to go put the electrons. And then there's still 2 more electrons, so you're just going to put them over there. Okay, now if I had to draw another NH3, then, and we always draw 2 because we're looking at the intermolecular forces, which is the forces between the molecules. So it's the forces in between them. Okay, so that's ammonia. So there's 2 ammonia molecules. Now, if we do phosphine, which is just pH3, then I'm going to take the periodic table away now, but just have a look at that. It's also in group 5. And so it would look something like this. And then I'll draw another one. Okay, so that is what phosphine would look like. Okay, now if we look at this NH3 molecule, we can see the electronegativity of hydrogen is 2.1 and nitrogen is 3. So the electrons are going to be more towards nitrogen. Okay, so and then if you want to get super technical about it, these lone pairs of electrons are actually going to cause these hydrogens to move further away. So your molecule would actually, now this is just me being technical for those that were wondering, but you can definitely just leave the diagram like that. But for those of you that are wondering, these electrons would actually push these pairs further away, and so you could also draw it like this. You could have it like this, like this, like this, and like that. See, so these electrons, this hydrogen, those hydrogens with its electrons have been pushed a little bit further away. Okay, but just to keep things basic, I'm going to leave it like this. Now, if you look at the net dipole moment, well, the electrons are going to move this way, and that way, and that way. Okay, and so if you look at those arrows, are they going to cancel each other out overall? No, they're not. There is going to be a net dipole moment. So this molecule will have a net dipole moment. If something has a net dipole moment, then it is polar. So here we have 2 polar molecules next to each other. Okay. Now, if you had to go do the same thing over here, you are also going to find that this is going to be a polar molecule, and this is going to be a polar molecule. Now, when you have a polar molecule and a polar molecule, the intermolecular force between that is called a dipole-dipole force. Okay, but you do also get a different type of dipole-dipole force when you've got polar molecules, and that is whenever you have hydrogen bonded to either nitrogen, oxygen, or fluorine. If you have hydrogen bonded to any of those, then you can get hydrogen bonding. And so here we have nitrogen bonded to hydrogen. And so this isn't only going to be dipole-dipole, it's actually going to be hydrogen bonding. And hydrogen bonding, because this is dipole-dipole, this would have also been dipole-dipole, but because of the nitrogen and hydrogen, this actually becomes hydrogen bonding, which is like it's a more stronger type of dipole-dipole. Okay, and so hydrogen bonding is much stronger than your normal dipole-dipole. So we would expect ammonia's boiling point to be larger than phosphine. Remember, these are negative values, so this is a larger value. This is a larger value than this one. Okay, now let's go explain the answer. So what you'll do is you'll say that you'll just mention what ammonia molecules have. So you can say ammonia molecules contain hydrogen bonding between the atoms. Between the molecules. Okay, your next thing would be to mention phosphine. So phosphine molecules, or let's just say phosphine. So you could just mention, for example, that ammonia contains, I don't know what I was going to write there. I was going to write phosphine. I don't know what ammonia. So you could start by saying that ammonia contains hydrogen bonding between its molecules. Then for phosphine, you could say phosphine contains dipole forces between its molecules, okay, you could then say that hydrogen bonding is stronger than dipole forces. You can then say, therefore, energy is needed to overcome the forces of attraction between ammonia molecules. Okay, I'm not going to fit that in. Ammonia molecules. This question says, define the term vapor pressure. So let's talk about vapor pressure a little bit. So if you have, let's say for example, you've got a pot filled with water, okay? And let's say you have a lid, okay? Because, let's put a red lid. And let's say the temperature is very low, so you mostly just have liquid water, okay? So here we have liquid. And what happens is when you start increasing the temperature, these little molecules are going to start getting energy. And what happens is that some of them start converting into the gas phase. Okay, so they start going into the gas phase. Okay, and that gas is the vapor. Okay, and it starts exerting a pressure in this area. There's a pressure. Okay, now eventually some of the liquid molecules are going to turn into gas, and some of the gas turns back into liquid, and we get some type of reversible scenario happening, and this system reaches equilibrium. It reaches equilibrium. At that point, if you had to connect a little pressure gauge over here and measure, let's say you had to measure what the, like a little needle over here that measures the pressure, that pressure is called vapor pressure. So what is vapor pressure? It is the pressure exerted by a vapor which is in equilibrium with its liquid in a closed container. So it is the pressure that is exerted by the vapor which is in equilibrium with its liquid in a closed container. Okay. This question says, which substance in the table above will have the lowest rate of evaporation? Okay, so that's something that's not a very common question, but let's go explain it. So let's say you have a liquid, okay? I'll use water again. So here we've got these water molecules floating around in the liquid phase, and in between them are intermolecular forces. Okay, your London forces, dipole, hydrogen bonding. So that's what we've got between molecules. Now, let's say we've got this molecule here. Now, this molecule would like to evaporate. What does evaporate mean? It means it turns from a liquid and it goes into the gas phase. Okay, like water in a swimming pool, the level of water becomes less because some of the molecules can go into the gas phase even before the water boils. Okay, now for this water molecule to be able to go into the gas phase, it would have to overcome this force of attraction that is holding it to these other water molecules. So if these forces are really strong, then the rate or the speed of evaporation will be very low, because it'll be very difficult for these molecules to have enough energy to overcome these forces of attraction. So let's write that down. This is not part of the answer. This is just for yourself. If the intermolecular forces, I'm just going to say IMFs, are strong, then the molecules, or let's rather say, then it is difficult for molecules to overcome the forces of attraction and evaporate. Okay? But now if these intermolecular forces are weak, like if this force is not very strong, then it'll be very easy to overcome those forces and go into the gas phase and evaporate. So it says here, which substance in the table will have the lowest rate of evaporation? Or let's just say here, low rate of evaporation. So if you look at these boiling points, we can see that this one has the highest boiling point. This one has the lowest boiling point. So that means that this one is very difficult to separate. Difficult to boil. You can say difficult to boil because it's got a high boiling point. So you need to have a high temperature to convert to boil everything. This one's easy to boil. Easy to boil. So that means that this one's the one that's difficult to boil has very strong intermolecular forces because the molecules are holding on to each other very strongly. So it's difficult to boil or evaporate, if you want to think of it. It's the same. You can think of it in the same kind of way. We're looking at the strength of the intermolecular forces. This one's easy to boil. Look how low that temperature is. So this one has very weak intermolecular forces. So which of these substances would be the most difficult to evaporate? Well, that would be water, because the intermolecular forces are very strong. So that means that its rate of evaporation would be very low. And so the answer for this question is water. But now we need to explain why. So we can say that the answer is water. We could say it has the highest boiling point, which indicates it has the strongest intermolecular forces. We could then say that strong intermolecular forces leads to a low rate of evaporation. This question says, explain why iodine is not soluble in water by referring to the intermolecular forces in each substance. Have you ever heard, maybe your teachers mentioned this thing that's called like dissolves like? Well, this question is sort of having a look at the same type of theory. So if we look at water, it's actually really easy, this question. Have a look here. Once I show you this, you'll see it's actually really simple. So there we got a container and it's filled with water. Okay, now water is like this. And let's make it a larger container of water. And let's do another one. Okay, now let's say we try to put in some iodine. Okay, so we throw some iodine into the solution. So there's iodine. Now we actually only need one water molecule and one iodine molecule. Now let's see if these two substances are going to be attracted to each other, or are they not really going to be attracted to each other? So if you look at water, we know from our periodic table that the hydrogen is least electronegative, so that's very positive. The oxygen is very negative, and this hydrogen is very positive. So it's got this clear positive, negative, these areas, okay? It's a polar molecule. Water is a polar molecule. If you look at iodine, however, it is a non-polar molecule. There is no positives and negatives. I mean, yes, you might get a little bit of positive and negative happening every now and then due to the random movement of electrons, but in general, this is a very non-polar molecule, so it doesn't have a more positive and a more negative part. So is there any reason then that this molecule would be attracted to this molecule? Not at all. There is no positive and negative over here. So these two molecules, this one and this one, are not going to be attracted to each other. So what that means is that when you put iodine into water, it's going to form a layer of, it's going to be like oil and water, for example. So you're going to have you might have the water, and then you might have an iodine layer over here. So this would be your iodine, and then this would be your water underneath it. So this would be your water layer over here. So they're not going to mix nicely together. And so what they say is that it is not soluble in water. You cannot mix iodine into water. It's almost like trying to put oil into water. It doesn't create a nice mixture, or it doesn't create a nice solution. You can see the different layers, and that's because they're not mixing nicely together. Like imagine if you took Oros and you threw that into water, and the Oros just stayed at the top or at the bottom. That wouldn't be really good, right? But because Oros is soluble in water, as soon as you mix it, it all creates one solution. It doesn't create different layers. So what we can do is we can say that iodine molecules are non-polar, whereas water molecules are polar. And then we can just say that polar molecules and non-polar molecules do not mix.